Is my screen visible to everyone?
Yes,
Yes,
sir.
yes, sir.
Okay. So what I will be saying now, I will be giving a lecture about ANOVA. This is a very interesting topic, and we will be discussing the basic assumptions of ANOVA, what kind of problems are required to run ANOVA, and how is it an extension to t-test. I'm sure that you have already heard of t-test and pair t-test also. So we will be discussing about one-way ANOVA, two-way ANOVA, and hopefully if we have time, we will be continuing with repeated measures ANOVA. Okay, so let us start now. And if you have anything to say, you can speak in between or you can write in the chat box. I will check it um, by switching to my window then. So first of all, I will just give a brief introduction about why we need inferential statistics, why we need to have certain objectives according to our problems, and what kind of tests are suitable, and why ANOVA is suitable to certain kind of problems. So first of all, uh, types of statistics, you all know that. I'm sure that my lecture is after, I think this workshop has already started last week. So you have probably learned a lot so far. And I'm sure that some of these concepts you already know. So it will be a good revision for you all. So first of all, types of statistics will be about descriptive and inferential. So if you have to describe any data, the most important concept about any data analysis is you have to describe your data to those audience or to those individuals that are not familiar with statistical concepts. Okay, so describing your data means that you have to extract as much information as you can about your data. So that will be considering summarizing and describing your observations. So if you consider mean, median, standard deviation, central tendencies, all of those measures of dispersion, all of these concepts, they will be considered under descriptive statistics. And they are known as, if you suppose know the value of a mean, suppose you know the value of standard deviation, these are exact values and they are known as point estimation. Right. So point estimation means that you know the exact value of those statistics or parameters. Statistic will be if you consider the sample, parameters will be if you consider the population. Okay. Second type is inferential. That is how you can make inferences about a larger number of individuals based on a smaller sample. So this will consider the concept of sample and population. So every one of you must know that sample means you consider a subset of a population because we do not have enough money or resources or time or human power to collect information from all of the whole population. So therefore we consider a small subset and we work on that. And based on the observations or outcomes we observe from the sample, we make inferences about the whole population. Right. So making inferences from a known sample to an unknown population, that is what statistical inference is. Right. For example, suppose if someone says that he cycles for about 50 kilometers per week on average, that is a direct value. Right. And if you are making inferences, then the second example is we can expect a lot of rain this time of year. So that is inference. You are making based on your prior information, based on some previous scenarios and based on some previous trends, you have to make inferences about the future. So that is considering the second step. Then ANOVA considers, it is the second step of hypothesis testing. The first step is considering when you only have two groups. So two groups, the first step of hypothesis testing is when you only have two groups, and in that case you have to apply t-test, or suppose one sample t-test, or suppose paired t-test. So these are the parametric alternatives. The non-parametric options are the non-parametric options are Mann-Whitney test, Kruskal-Wallis test, and Wilcoxon-Sign rank test. So what you have available for your parametric test, that is, you need to know the difference between these two, and we will consider them in the next few slides. So hypothesis testing is interpreting results. And first of all, I will consider this slide. And after that, I will show you a real life problem and we will run that in SPSS. Okay. So hypothesis testing is interpreting results obtained from a sample and making inferences about a population. Right. So as I've said in my earlier um, uh, a few minutes, that you need to use the sample and you need to make observations or inferences about a population. So you are going from a known sample to an unknown population, and this is known as statistical inference. And in the end, you conclude whether the results are significant or not. Significant means that important. So if whether the results are important or not, and we will be using the concept of statistical significance. If some of you are from medical background, then you know that the concept of clinical significance is also there. So statistics, statistical inference, hypothesis testing, whatever concepts you have, regression analysis, correlation, all of these concepts, whatever results you obtain, they might be very common sense, they might be very easily available, but the thing is you need these concepts to validate your results. So if you have, you know that there are mean differences. Suppose two groups, two classes, the marks of two separate classes, they are different, and you know that one of the class has an average of marks, suppose 50%, the other class has suppose 75%. So by saying this, you know that there is a an obvious difference between the two means. So what you have is you need validation from statistics also. So statistics not just only looks at that 50% or 75%, but it looks at the each of the individual that appeared for that exam. Okay, so population versus sample. Population refers to all of the cases. This is just a very introductory concept, and sample is used to study some part or subset of the population. Descriptive statistics simply summarizes a sample, and inferential statistics generalizes from a sample to a broader population. Next, whenever you collect data, you will have variables, and samples are made up of individuals. Whatever information you collect from the individuals, those are known as variables. The variables can be, suppose, if you're measuring height, if you're measuring the gender, if you're calculating weight, if you're calculating BMI, if you're calculating age, all of these will be variables, and these are known as variables because the values will change for each individual. Next, we have the concept of parametric versus non-parametric. So hypothesis testing uses the concept of both parametric as well as non-parametric. The difference between the two topics is that parametric takes the assumption that the data needs to follow normal distribution, and non-parametric tests or techniques that are available, they do not have such assumption. That is, you do not need to check whether the data is following normal distribution or not. Right, so it is also known as, these tests are also known as distribution free test. So but parametric tests are more powerful because they are based on normal distribution, and normal distribution is the most common, most widely used continuous distribution throughout every single real life problem. Even the discrete distributions that are available, suppose binomial, they can also converge to a normal distribution based on certain large sample theory. Okay, so I'm sure that you must have heard of central limit theorem. Central limit theorem states that according to central limit theorem, if you have a large sample, then any data will follow normal distribution. So if you have to apply t-test, or if you have to apply pair t-test or ANOVA, then the normality assumption needs to be met. Otherwise, if the distribution or the data is not following normal distribution, then you have to either transform the data by using certain techniques. The most common one is Box-Cox transformation. You can use that to transform the data into normal and then apply the test. Otherwise, you have to go for the non-parametric options then. The test will be Mann-Whitney, Wilcoxon test, and Kruskal-Wallis. These are again what I've just said. These are the differences between the parametric and the non-parametric. T-test has an alternative non-parametric of Mann-Whitney. Within subject t-test, that is when you are analyzing within the subject variations, those will be alternatively calculated from Wilcoxon sign rank test. And ANOVA is non-parametric availability is Kruskal-Wallis. Right, so hypothesis testing uses the concept of null hypothesis and alternative hypothesis. I'm sure all of you know this. Null hypothesis is by default set previous to any problem, and if it is set previous, that is, it will always consider that there are no differences among your values. Okay, the parametric test, let me mention the parametric test, whether it is t-test, ANOVA, or pair t-test, they are all mean based. That is, they are focusing on the differences of the means among the groups. And the non-parametric, they are all median based. So non-parametric are median based, and they will be comparing the medians of the data of the certain groups. Okay, so test of significance will be, you have all of these tests, and in the end you will conclude whether to accept the null hypothesis or to reject it. Now make sure that your conclusion will always be on the basis of the null hypothesis. The null hypothesis will always consider that there is no difference among the parameter values, right? Again, two things you need to remember. Null hypothesis will always consider no difference among the parameter values, and I'm mentioning parameter values. That means that the null hypothesis and the alternative hypothesis, they will both consider parametric values. That is the population values. Parametric or parameters, they refer to population, whereas statistic, they refers to sample, right? If you're talking about a sample mean or a sample standard deviation, they are known as statistic. If you're talking about a population mean or a population variance, those are known as parameters. So the hypothesis, both null and alternative, they will consider population values. Okay. So null hypothesis is a statistical hypothesis that is tested for possible rejection under the assumption that it is true. It is tested for possible rejection under the assumption that it is true. So if it is true, and suppose we reject it, that is a type 1 error. Okay. And if you are accepting the null hypothesis but it was false, then that is a type 2 error. So I'm mentioning this because we use the concept of level of significance, which is denoted by alpha. And if it is denoted by alpha, then it is set at either 1%, 5%, or 10%. Okay. So level of significance, and we come is the probability of conducting a type 1 error. Okay. So the purpose of most statistical tests is to determine if the obtained results provide a reason to conclude whether or not the differences are the result of random chance. That is, we need to minimize the error. First of all, the main concept of every single statistical concept is to minimize error, and then focus on whether you're focusing on differences, whether you're focusing on relationship or association. Then whatever tests are applicable or suitable, you have to focus on that. So if you reject the null hypothesis, that means you will accept the alternative hypothesis. And this is just a summary of the type 1 error and type 2 error. Level of significance alpha is setting the standard for how extreme data must be before rejecting H naught. In simpler words, it just means that if it calculates the probability of type 1 error, that is, the probability lies between 0 to 1. Okay, so what is the probability that a type 1 error will be conducted? And every single problem or every single research objective or research problem will have errors. There are no studies or no problems in the world that do not have errors. So we set this before conducting the analysis or before even conducting the experiment, because we need to mention that this is the allowable error. Level of significance is the allowable error. If we fix it at 5%, then it means that 5% there will be error in the study, and that is fine. That is fine. This is the amount of error we are fixing before the study. So how do you decide whether you have to reject or to accept the null hypothesis? It is based on p-value, and p-value is the result or output in any software, whether it is SPSS, Minitab, R, Python, any software, Stata, Excel, whatever you are using. Every single test will provide a p-value. You have to compare that p-value with the level of significance alpha. If the p-value is less than equals to alpha, then you reject the null hypothesis. And if it is greater than alpha, then you accept the alternative hypothesis. Sorry, then you accept the null hypothesis. Sorry. If it is less than equals to alpha, then reject null. If it is greater than alpha, then you accept the null. Okay. And this is, if you reject the null hypothesis, you conclude that you have rejected the statement there is no difference or both are equal, right? So no difference, both are equal means the same thing. You have rejected that. So in the end, that means there was a difference. So if there is a difference, that means you are statistically, what you have to say is that there is a statistical significance between the groups, or that there is a significant difference between the means, between the variances, whatever you are testing. Okay. So this is a very important concept, and whatever test or analysis or concept you are learning in this workshop, every single concept uses the p-value test or technique. Okay. So p-value, what is p-value? It is a probability of the actual rejection. So in other words, it is the actual level of significance. I don't want to confuse you. I'm saying that you have alpha, which is the level of significance, and you have p-value, which is the actual level of significance. Okay. So any software will provide this, and you have to base your conclusions according to this. So I'm covering the topic of ANOVA, but just a brief introduction. ANOVA is only used to compare means and if there are more than two groups. When you have to compare means of more than two groups, then you have to apply ANOVA. If you have two groups, then you have to apply t-test, and that is also known as two sample independent t-test, right? So you have, if you have before and after values of the same individuals, then that is a concept of paired t-test. If you only have one group, then only one sample t-test will be used. If you have two separate groups and you have to compare the means of those, then you have to use or apply independent sample t-test. So it is used to compare the means of two groups when the data is following normal distribution. Okay, so am I clear to everyone up till this point?
Yes,
Clear,
sir.
sir, clear.
Okay, I hope that everyone is understanding what I'm explaining. So we will show you. I will show you how to run an ANOVA in SPSS and also how to show the t-test. If suppose you have the data in which you have to apply ANOVA, but then you cannot forget, you cannot exclude the concept of t-test because the t-test concepts will be used in ANOVA also. So independent sample t-test compares the mean. You can read the last line that compares the means of one variable for two groups of cases, right? This is known as between participants design. One sample is when you only have one group and you have to test the mean with a particular value. Suppose if you have collected height of suppose 20 individuals, which in centimeters, and you want to test according to the sample. You want to test that based on this sample, the population mean will be equals to 170 centimeters. So as I mentioned earlier, you are using the sample to make your conclusion about the population parameter. So based on the sample, you are testing whether the population mean will be 170 centimeters or not, right? So that will use the concept of one sample t-test. Two sample will be, suppose you are dividing your study according to male and female, right? So the average height in population for males is 175 centimeters, suppose, and the average height of females in population is 165 centimeters. Suppose we want to test that. So if we, or we can also test that this will be considered. Let me just write. Let me show you first of all the concept. What I want to test is if suppose I have my null hypothesis, this will be set at mu1 is equals to mu2. So mu1 is the population mean of the first group and mu2 is the population mean of the second group. Alternative will be, there will be three cases, either not equals to, both are not equals, one is less than the other, and these will be based on two things. Mu1 is greater than mu2, right? So the alternative has three cases that either the both values are not equal or one is smaller than the other. These, the ones that are smaller than the other, they are known as one-tailed test. And this one is known as two-tailed test, the not equals to one, right? So if you're comparing the heights of males and females in two separate groups, then you have to use this concept of null and alternative hypothesis. And in the end, according to p-value, you have to accept or reject the two. So if the null hypothesis will always be equals to, or I can write this as mu1 minus mu2 is equals to 0. That is also the same thing. Either you state that there is no difference between the two or you state that both are equal, right? So this is the concept of t-test because I'm using only two groups. If suppose I extend this and suppose I have three groups and I want to compare the means of those three groups. So my null hypothesis will be mu1 is equals to mu2 is equals to mu3, right? And my alternative hypothesis will be that at least two mu's differ, right? So either the difference might be between mu1 or mu2 or between mu2 and mu3 or between mu1 and mu3. All possible combinations have to be considered. So ANOVA will only provide you the acceptance or the rejection of the null hypothesis, and you have to run some additional tests in order to finally analyze whether where is the difference actually lying, whether is it between mu1 and mu2 or between mu1 mu3 or between mu2 and mu3, right? So alternative will be at least two mu's differ. right? So this is the concept of ANOVA, because if I have more than two groups, then t-test will not be applicable, or it will be applicable if I consider it, if I run the t-test one by one. So that will be more time taking. I can run the t-test. I can run the t-test. First, I will run and compare the values of mu1 and mu2. And suppose alternative will be not equals to these two values. Second test will be mu2 is equals to mu3, and alternative will be that they are not equal. And the third category or combination will be mu1 is equals to mu3, and otherwise this is not equals to. So if I have to run this one by one, this is the first combination, this is the second, and this is the third. If I have to run these, then I have to apply t-test one by one. So I have to apply t-test three times. So in order to save time, I will apply ANOVA, and that will make all of these calculations in a single take. Okay. So I will have to just apply it only once, and it will provide me the result of, suppose I am running the t-test three times, and I will get the same analysis results by running a single concept of ANOVA. Okay. Then I will be showing this in SPSS. Suppose how do you, this is just a brief screenshot of how you operate SPSS. You have to go to, first of all, analyze, then compare means, and then if you're running paired t-test, in compare means, you have all of these options. You have means, you have one sample t-test, independent sample t-test, paired sample t-test, and one-way ANOVA. For two-way ANOVA, there is a different direction of concept or procedure, right? So if you have to apply independent samples t-test, then you choose that option. If you have to apply paired t-test, then you choose that option. If you have to apply one-way ANOVA, then it will be the last option. Then that, suppose I'm just showing you an example, I will show you a real life data also. Suppose paired sample t-test, in the end, all I have to do, you do not need to understand what the problem is. You have set the null hypothesis to be that there is no difference, or suppose the instructions have made a difference, right? So in the end, all you have to do is look at the p-value, which is denoted in this red circle on the right side of the output table, and that is denoted, the SPSS output will not consider p-value, it will write SIG, right? And it is automatically showing you a two-tailed. That means the alternative hypothesis is not equals to. Okay, so not equals to, and then there are additional results also, like 95% confidence, mean, standard deviation, standard error mean, and then the t calculated and degrees of freedom. So all of these are options available. How many of you know the concept of paired t-test, if I ask? Let me just check the chat box up till this point. Okay. All of you know the concept of t-test, paired t-test also? Are you familiar with t-test? First of all, let me ask that. It's same for the, it is for the same individuals tested twice, right? If you are testing the same individuals but at different time points, that is, suppose before you have been given a medication, some reading has been noted, and then after the medication has been given, some that reading is again noted, and you have repeated this for suppose 20 to 30 individuals, right? So if you're considering before and after values, then paired t-test will be applied. Another example is that if a new semester is starting and you take the examination, or suppose a surprise test at the start of the semester, and you note that will be the before semester, and in the end, after the semester, or suppose 3 months and covering of all 4 or 5 units as much as the syllabus, then you take the examination again, that will be after covering the syllabus. So then you can compare the before and the after values in the marks, right? Okay, so all of you know the concept, right? If you have to apply one sample t-test, the concept is same. I'm not going to go through this. And if you have to apply a two sample t-test, then you have to choose the highlighted option, independent samples t-test. And how you run it, I will show that. And you have to first of all define, I hope that defining variables and defining discrete variables is already explained by the previous sessions. And let's move on. So in the end, the output will look something like this. What you have to look at, either when you have to apply a two sample t-test or you have to apply an ANOVA, then you have to first of all check the assumption of homogeneity of variance. Okay, so if equal variances are assumed, then you have to consider that particular p-value. Suppose, how do you consider variance? All of you know the concept of variance, that is the distance from the mean, the squared average distance from the mean. That is the exact formula. And let me explain. All of you know the topic or the full form of ANOVA? Can someone tell me the full form of ANOVA? Okay, it is analysis of variance. Variance is given by, suppose variance of x, you have 1 upon n. I'm calculating the population, and if I'm denoting it simply as xi minus x bar, this can also be written as mu and whole square, right? I is equals to 1 to n. This is the formula of variance. And what is it? It is actually the difference between xi and x bar. Forget the summation, forget the square. It is the difference or the distance of every single value, that how far every single value is from the mean, from the population mean. So then you square it, then you take the average of it. So you're looking at the squared average or the squared distance of every single value. If I explain it graphically, or you can take the under root of it, standard deviation will be what? The under root of variance, right? Standard deviation will be the under root of variance. And let me explain. Suppose, I don't know if you have already studied regression or not. You have some points plotted and you draw the line of best fit, right? If you have a line of best fit like this and all of the points are lying on the line, then that is a perfect relationship between the two variables. What the variables are? X and Y. They can be height and weight also. So, but looking at these, what variance or standard deviation is the distance of this point from this line, the distance of this point from this line, and the distance of every single point from the line, because the line that will always pass through the mean values of x bar and y bar. That line will always pass through the mean value of x bar and y bar. Therefore, every single point is how far it is from that line. That is the standard deviation. Or in other words, in regression, we call it error or residual. Or in another words, we call it loss of information. Okay, or loss function also, because these are the values which are far away from the line, and that means they are somewhat different from what we have wanted or we want for our exact or perfect result to be. But we do not observe that in every single experiment or study. Therefore, because results or errors are there in every single result. Okay, so this is the concept of variance. And because analysis of variance uses the concept of mean, therefore we set the null hypothesis as comparison of means. In this, the name suggests analysis of variance, but we are comparing all, as many groups as we have, we are comparing the population means. We are not comparing the variances, because the variance is using the concept of mean. We have single value or every single value, that how far it is away from the mean, and then we calculate the variance. So if the mean is changing, then obviously variance will also change, right? So don't get confused by the name that we are analyzing the variance, but why is it that we are comparing the means and not the variances? If you change the mean, then automatically variance will also be changed, right? So let us move on to ANOVA. It is of, what I have to cover is, it is of two types, one-way ANOVA and two-way ANOVA. One-way ANOVA means that we only have one dependent variable and one independent variable. That is, we only have one group on which we are dividing our data. Again, suppose you are calculating height of 30 individuals. So that can be 164, 174, 184, 155, something like that. And you have also calculated, or you have also noted down the gender. If the person is a male, female, according to this, right? So you have to compare whether the null hypothesis will be mu m is equals to mu f. Now this is only two groups, so we have to use t-test and not ANOVA, but the concept is the same. You have to compare the population means. That is, you have to compare based on this sample, you have to compare the population means of height values of males and females. Okay, so when you only have one categorical variable, this is known as a categorical variable because it is not a continuous type, it is a discrete type of variable, and it only has two categories, either male or female. There can not be no other possibility for this variable. And suppose I include another variable of income, and that can be divided as a very low income, uh, middle income, and what else? High income, we can say that, right? High income. If I have a second, this is also a categorical variable, this is also a discrete type, but how many categories do I have? Four I have. So if I want to compare the height based on income, then t-test will not be possible, and I have to apply a one-way ANOVA, right? So one-way ANOVA means you only have one independent variable or one categorical variable on which you are dividing the continuous values of. Okay, this is the difference. If you have two variables, suppose two independent variables on which you are dividing, or you have two set of different groups, then that will be known as a two-way ANOVA. In another words, you can say that how many factors you have. So if you have only one factor, then it is one-way ANOVA. If you have two factors, then two-way ANOVA. If you have three or four factors, then accordingly it will be a three-way ANOVA or a four-way ANOVA, right? But we are not covering those. Right? So if there is only a single factor available, and analysis of variance is used to test the hypothesis that several means are equal. I've already explained this. This technique is an extension of the two sample t-test. In addition to determining that differences exist among the means, you may want to know which means differ. There are two types of test for comparing means: a priori contrast and post hoc test. So I mentioned that ANOVA will only provide you the result of whether you have to accept or reject the null hypothesis. That's it. You will only know after running an ANOVA, you will only know whether a null hypothesis is accepted or if it is rejected. So if you accept it, that means all of the three groups are equal, right? If you reject it, then all of the three groups are not equal, right? Somewhere there is a difference between the two groups. Okay, but how do you find out that difference? That is found out by applying a post hoc test. Okay, a post hoc test, or it is also known as it is also known as either you have to name it post hoc test, or you can say multiple comparisons. You should understand by multiple comparisons, it means that you are making multiple comparisons. That is mu1 with mu2, all of the three combinations which I've explained, mu1 with 2, then 2 with 3, and then 1 with 3, right? So if you have more categories, then more combinations will be formed. But it is only considered to be pairwise. Okay, so that is the concept. That is the concept of additional testing of significance. If you have to find out, suppose where's the difference lying between the groups, and this is only possible or this is only suitable when the null hypothesis is rejected. Because if the null hypothesis is rejected, only then you have to find the post hoc test or the multiple comparison. Okay, assumptions, these are very important. If you do not meet these assumptions, then you cannot apply ANOVA. And I'm suggesting this to all of the participants because many students, they come from different departments and they want to apply t-test or ANOVA. They do not check whether that is a suitable test or not. You have to first of all check for the assumptions also. And these assumptions are required in all of the concepts. Suppose if you are running a regression, then you have to run this last stated one, ordinary least square assumptions, right? That is a concept of regression, but it is also required in running an ANOVA test. Okay, so the dependent variable needs to be continuous. That is your height variable, weight variable. It is supposed to be that is known as a dependent variable, and it needs to be continuous. And then you have at least one categorical independent variable or known as a factor. If you have one, then one-way ANOVA is applied. If you have two, then two-way ANOVA will be applied, and so on. Observations need to be independent. The groups should have roughly equal variances. This is again considering the homogeneity of variances concept. Then the second last one is the data in the groups should follow a normal distribution. And if the data do not follow a normal distribution, then either you have to transform that data or you have to apply a non-parametric Kruskal-Wallis test. And last one is residuals satisfy the ordinary least squares assumptions. Do you know or are you familiar with the ordinary least square assumptions? What does that mean? You must be familiar with this equation. What is this? This is a line equation, simple equation of line, right? Or it is also known as beta naught plus beta x. Okay, sometimes it is also known as beta 1x. This is the intercept and this is the slope, right? So y is equals to beta naught plus beta 1x plus epsilon. This epsilon, this is known as the residual, and this epsilon, the concept is it will always follow a normal distribution with zero mean and a constant variance sigma e square. That is the concept of ordinary least square. That the error variable or the residual, it follows a normal distribution with zero mean and a constant variance. And therefore, for a linear regression, this y variable also follows a normal distribution. Forget about the zero mean and variance constant. Forget about that. But y variable needs to follow a normal distribution. You must have already studied about logistic regression in that y variable needs to follow a binomial distribution, right? I'm sure that you must have studied this in the previous session, and that is required. So according whatever y variable is, that particular regression technique will be possible, right? So this is the last assumption, and all of these assumptions, the majority one that you have to check is for the normal distribution and also for the equal variances and the data is continuous. These are the most important ones. Okay. So hypothesis testing. This is the difference between a one-way ANOVA and a two-way ANOVA. In general, the null and alternatives are defined above. Null hypothesis will be that all of the means are equal, that is all of the population means are equal. If suppose you only have three groups, then this will only go up to mu3. And the alternative will be at least two mu's differ. The one-way ANOVA model is defined as yi is equals to mu plus alpha I plus ei. And two-way ANOVA is defined as, because in two-way, in one way you only have one factor and that is denoted by alpha I. In two-way, you have an additional factor of beta, so that is also added into the additive model. That is mu plus alpha I plus beta j, and then the last term will be error. So hypothesis will be based on alpha I and beta j. What do I mean by that? So these are all very important before you run any. See, the software will always provide you the results. You need to know the theoretical concepts and why you are testing that, and plus also the assumptions. If you do not check all of these, then the software will not be able to provide the correct results. So you have yi is equals to mu plus alpha I and then plus epsilon I. For two-way, you have yij is equals to mu plus alpha I plus beta j and then plus epsilon ij. Okay, so mu is the general mean. This is also known as one-way ANOVA. This is the model for that, and this is two-way ANOVA. Okay, so general mean is mu. Alpha I, that means the whatever single factor you have, you are comparing the effects of that. So the null hypothesis will be alpha 1, sorry, this is 1, this is equals to alpha 2, this is equals to alpha 3, and so on. This is all equals to, suppose, alpha up to n, right? And alternative will be at least two alphas differ. Two alpha i's, they differ. In two-way ANOVA, you will have two set of hypotheses. One will be for alpha I, and then the second one will be for beta. So second one, in that, first of all, you denote alpha naught alpha and H naught alpha, and the alternative will be defined as HA alpha. Then for beta 1, you have H naught beta and you have HA beta. Okay. Now this one will be regarding the beta effects, the effect of the second factor whichever you are testing. So beta 1 is equals to up to suppose beta L, and this will be at least two betas will be different, right? So ANOVA will two-way ANOVA will provide you both of these hypothesis results, and then you will have to make a proper comparison between whatever factors you are analyzing. Okay, so now up to this point, is everything clear?
Yes.
Clear, sir. Clear.
Okay, what about anyone else? Okay. Okay. So let us move on. And how do you run? Again, it is the same procedure to run a t-test. You go to analyze, then compare means. This is an SPSS. Compare means, and then the last option, one-way ANOVA. This another window will open, and you have to shift your variables accordingly, and you have to choose whatever option you want. You have to select those options, right? I will show that. This is a screenshot of running a post hoc test. So in the previous slide, you have seen that there is a red circle option of post hoc test. So you are telling SPSS that you have to run a post hoc test if the null hypothesis is rejected. But SPSS will provide a post hoc test even if the null hypothesis is accepted, because it is the programming is based such as that it will provide you all of the results, even those which are not required. So that is where your concept and your knowledge comes in, that you have to study every single table, plus you do not have to study every single table, because some of the concepts they are not required, and we are covering the basic only in this workshop. And plus your analysis, I hope that it will be only not too complex. So you only have to analyze or look at the or observe the basic part only. So like reject the null or accept the null, otherwise post hoc test, where is the difference lying? You have to analyze only that part. So you click on post hoc, and then this second window will open. And the best possible options are Bonferroni, Sheffy, and Tukey. These are the three most widely used. And suppose if equal variance is not assumed, we are considering there was one assumption that the groups or the 3, 4, 5, as many groups as there are, those should have about approximately equal variance. So if equal variance is not assumed, then there are these alternatives. The best one is Games-Howell test. So again, that is out of the course of this workshop, but I'm just suggesting it, and these are all uh, required concepts which everyone should know about ANOVA. It is not just simple that you have to analyze the population means and looking at where the difference lies. You have to look at the assumptions also. And if those assumptions are not met, then what are the alternatives? So in case that equal variances are not met, then you have to run a Games-Howell test. But you can still run a Tukey. It doesn't matter. It doesn't matter because if you have a large sample, then some of these assumptions can be excluded also. So when you run a post hoc test, the null hypothesis in ANOVA is rejected, and only then you run a post hoc test when the null hypothesis is rejected. But to know where specifically these differences are, that is why you require the post hoc, right? So thank you slide has come up first, but now that means that the presentation part is complete, and we will consider a data set. Suppose, consider this left side data set. I'm not considering this part. Let's shift that over there. So this is a, we have income of suppose 40 individuals. We have divided or we have noted down their male, whether their gender, whether they are males or females. Then we have looked at what subject they have studied, what degree they have obtained. So if they have obtained statistics degree, if they have a major in statistics, how much income they are earning? What is their annual income? Suppose if a person is from political science, what is their income? If a person is from psychology background, then what is their income? So we want to make a comparison between the income, suppose, and you only want to make a comparison between males and females, then you have to run a simple two sample independent t-test, two independent sample t-test, sorry, right? Because you are only looking at one factor, that is gender. When you will be looking at two factors, that is gender and the subject studied, then that will be required for ANOVA or two-way ANOVA when you are considering both, right? So two-way ANOVA is also possible in this, but one by one, let us consider this. So you have to define this data accordingly in SPSS. I've already done that to save time. First of all, you need to create three columns, right? So all of you are paying attention, I hope. All of you are following? Because we have covered the theoretical part, now we are moving on to the practical part. Okay. Remaining participants, please reply.
Yes, sir. Yes, sir.
Okay, so moving on to the numerical part. Uh, uh, Data defining, that is all, you are all familiar with that, how to define it. I have to define for running an ANOVA or a two sample t-test, you have to define the income in a single column. Okay, this is the requirement of SPSS. In the Excel file, now Excel file, always use Excel for any data handling or data manipulation because Excel is connected with all of the softwares. It is the best manipulation tool or the data handling tool there is, data editing tool, because it is connected with every software. Doesn't matter if you use SPSS, Minitab or R, but in this we are considering SPSS. So I'm defining according to that. So in this, the original data set defined that the income was separately defined in the three columns for statistics, political science, and psychology. And they are also defined row-wise separately for males and females, right? So now, but in SPSS, you cannot have three separate columns for income. You need to define the columns in a single. You need to define the income in a single column. Okay, so I have defined all of that. I have named it salary, and I have uh, entered all of the salary information, that variable, all of the values in this single column. And second one, you can see that the code is only 1, 2, 3, right? So which is it? It is for the subject. Subject means 1 will be for statistics, 2 will be for political science, and 3 will be for psychology. And SPSS, you can enter words and alphabets also, but those will be considered as string variables. But then in order to run the analysis, you need to define the codes. And you have already studied that. Without the codes, the analysis is not possible. And gender, there are only two possibilities, males and females, and we have defined the males by 1 and females by 2. In case you forget, you can always go to this variable view at the bottom, and here is the place where you have to define your variables. You have to name the variables. So salary, subject, and gender. The salary is a continuous type, therefore I have chosen scale. Subject and gender, they are both nominal categories because ordinal is not required in this, order is not necessary. So there is nominal type, and what each coding is, you have to define it in values. You have to define 1 for statistics, 2 for political science, and 3 for psychology. And similarly for gender also, male and female. Okay. Then go back to data view, and your variables will be defined. You copy paste from Excel all of the required data, but you cannot copy paste the males and females and the subjects. You have to enter that manually. You have to enter that manually. Another thing which I have to mention is the assumption of normality. Now you have to assume that if the data is following normal distribution, then only then ANOVA is possible. But you have to check the normality of the three income groups separately. Okay, you cannot check for this single column. You have to check the normality for the three columns separately. The three columns, statistics, income values need to be normally distributed. Similarly, political science need to be normally distributed, and psychology need to be normally distributed, right? So what you do or how you do it, you have to define a new data. because it is not possible in this. So new and then data, and you just copy paste the three columns. You can name them. Will be stats, then political science, and then psychology. And they are all scale type of variables. Right. So normality assumed or normality is tested according to two concepts. First is Shapiro-Wilk test, and second is QQ plot, or third is, these are graphical options. Histogram, there are many more. There is box plot. You can check the normality according to those also. And stem and leaf plot is also an option. Shapiro-Wilk test, this will provide you a p-value, and if this p-value is greater than alpha, or suppose 5%, we are setting our alpha at 5% by default. In all of the cases, we are setting it at 5%. So if the obtained p-value according to Shapiro-Wilk test is greater than alpha, greater than 5%, then the distribution is said to be normal, right? That is, you are accepting the null hypothesis for normality. The null hypothesis is data is normal, against the alternative that data is not normal. Not normal, okay? So data is normal, that is null, and alternative is data is not normal, and I want the data to be normal, therefore I want the null hypothesis to be accepted, and that is only possible when the p-value is greater than the alpha value, right? It is greater than 5%, that is, it is greater than 0.05. Then the three remaining options, those are for graphical or visualization. So let us run the Shapiro-Wilk test first of all, and this one. We have defined the data into three columns. Go to analyze, descriptive statistics, then explore the third option. Analyze, descriptive statistics, and explore. You have this new window open. Select all of your variables and shift them to the dependent list box, right? And at the bottom, you have to display both statistics and plots as well. So I want both, and go to plots. Here I want histogram and not stem and leaf. So select histogram, and I also want normality plots with test. This is the procedure for running a Shapiro-Wilk test. Okay, click OK. And in statistics, everything is fine. I'm setting the alpha at 5%, so that means confidence interval will be set at 95%. 100 minus 5% will be 95%. Click continue and then click OK. Just give it time to run the analysis. You have all of these three boxes. The first one is explaining whether you have any missing information or not, but no, you have 40 values in each of the three categories. 100% data is available. There are no missing options. Second one is your descriptive and stats, political science, psychology, all of the mean, confidence interval, trimmed mean, median, variance, standard deviation, quartiles, sorry, not quartiles, minimum, maximum, all of these are provided for the three columns. Then for political science and for psychology, what you have to look at is the test of normality table and the second column, Shapiro-Wilk. Now Kolmogorov-Smirnov is also provided, that is another test for normality. But the difference is Kolmogorov-Smirnov test, that is possible for any distribution, whereas Shapiro-Wilk test is only possible, it is only applied when you have to test normality. It was only designed to test normality. Okay? Kolmogorov-Smirnov, again I'll say this, Kolmogorov-Smirnov is for any distribution, that is whether it can be checked for normal, exponential, gamma, beta, Weibull, all of those. But Shapiro-Wilk test is only allowed for testing a normal distribution. So stats, political science, and psychology, you have to look at the last column, which is SIG, and that is 0.603, 938, and 0.507. All of these are greater than 5%. That is, all of these are greater than 0.05. Okay, so all of these are greater than 5. That means the null hypothesis is accepted. That is, the data is following a normal distribution for all of the three columns. So this is more reliable as compared to the visual options. because the visual options will only provide you an approximate or a near about result. But the exact information is obtained from the last column, the p-value which is obtained from the Shapiro-Wilk test. Is it clear, everyone, up to this point?
Clear, sir.
Okay.
Clear.
How many of you are studying this for the first time? Test of normality to Shapiro-Wilk test.
Many of us, sir.
All right, so let us move on now. So our first, the main assumption, okay, the main assumption of normality is met. We have found that out from the Shapiro-Wilk test. Just give it some time. Okay, so Shapiro-Wilk test provides a normal distribution for all of the three variables. Another graphical option is you can look at the histogram. If the shape of a normal distribution is a bell shape, the shape of a normal curve, it is somewhat like this. So if your histogram, that is frequencies, that means that the bars need to follow somewhat this shape. Okay, so if it is following something like that, then you will say that the data is following normal distribution according to a histogram. So this is somewhat following a bell-shaped curve. Then if you look at the QQ plot, it is a straight line. And if all of the points or majority of the points are lying on this straight line, then the data is said to be normal. If there is a deviation, then the data is not normal. Detrended you can ignore. Box plot is, if this is a box plot, the bottom line is a minimum, top line is a maximum, and the center box, that is providing the 50% of the data. The lower line of the box is the first quartile, the top of the box is the third quartile, and the middle line, this bold one, that is median or second quartile. So if that second quartile or median lies exactly at the center of this box, then the data is said to be normally distributed, because the data will be symmetric, and a normal curve is a symmetric curve. So approximately this is also lying at the middle of the box, so we can assume a normality assumption is fulfilled. This is for political science, and it is a much better graph as compared to the statistics one, right? So this is, if you draw a line, it is having a high kurtosis and in the middle. So, but it is a much better approximation of a normal distribution. QQ plot full form is quantile, and majority of the points are lying on that line. And similarly, box plot shows a middle line at the center of the box, and this is for psychology. Now, this is not that well um, provided result, but we have a confirmation or a validation from the Shapiro-Wilk test, and that is providing the exact information that the data is following a normal distribution. So in case, that is why Shapiro-Wilk test is more reliable as compared to these graphical options, because these graphical options will provide you an approximation only. Okay, so you can see that for psychology, there is a gap here, and plus the data was lower side, and then it increased, and then again came back to the lower side, and that is what the normal curve is. It starts from the lower side, then increases, and then comes back to the lower side. Okay, so where this gap is, you can see that the deviation from the normality is observed in the QQ plot. If these points, they are lying away from the line. Suppose these points, they are also lying away from the line. So this is the portion where the normality is not met. But that is fine according to Shapiro-Wilk. Whole variable is following normal distribution. Right, so the normality assumption is met. So we have obtained that by running these analysis in separate three columns. Now, coming back to the original data. Now, suppose if you want to run a t-test, what you have to do? Why will you require a t-test? You will require a t-test when you want to look at income, or you will require a t-test two groups. Suppose you have male and female. So if you have two groups, males and females, then you will require, and you are analyzing income, right? So if you're analyzing income based on divided according to males and females, then you have to apply t-test because you only have two groups, amongst which you have to make a comparison that mu m is equals to mu f for males and females against the alternative that mu f is not equals to mu, right? So I have to analyze this, and we will run the, first of all, we will run the t-test. So I have this income column variable, and I have the gender, the third variable. Suppose I want to run this first of all. So go to analyze, then compare means, then independent samples t-test. The new box will open, select salary and shift it to the test variable box, and in the grouping variable, you select gender. Now there's a question mark for both of the values because it needs to define which of the values you are using. So define groups, and then here you have to select the values which you have defined in the variable view. One was for males and two was for females. Click continue. Check the options. There is no need to make any changes. It is set at 95%. Click continue and then click OK. That result will appear in the next window. So first of all, it says that t-test to show that you have run a t-test. So in order to first of all analyze whether all of the data is provided, the mean, the standard deviation, you look at that this group statistics table, the first table. It shows you are analyzing salary based on gender, males and females, and each of the groups has 60 and 60. They can be different also. There is no requirement that both of the number of males and females have to be equal. They can be different also. Then the mean salary of the males is 69,766. Similarly, for females, it is this much. Standard deviation is provided here. You have to look at the second table, the independent samples test, and you have to look at, first of all, the p-value for Levene's test for equality of variances. Again, the equality of variance assumption is required for t-test as well as for ANOVA. So for t-test, it is applied through Levene's test, and if the p-value is greater, that means, can anyone suggest what will be the conclusion? What will you have to do? Whether you will reject or accept the null hypothesis, considering this 0.147. Accept, right. The p-value is greater than level of significance, that is 5%. Therefore, you will accept the null hypothesis and you conclude that there are equal variances. So when equal variances are considered, then you will consider the top value where my mouse cursor is right now, this 0.005. You will consider that p-value for the t-test. If this Levene's test p-value was less than 5%, then you will consider the second one, the second row, equal variance is not assumed, and you will consider that particular respective p-value. But in this case, both of the p-values are same, so there is no difference among the two. But in other terms, this is not possible. Some other problems, it might not be possible, so you need to know the concept. So in this case, now looking at equal variance assumption has been followed, and then you have to look at the p-value from the t-test. So t-test provides also a significant result, that is the p-value is less than alpha, and you conclude that the null hypothesis is rejected. That means the null is rejected, and you are concluding the alternative to be true, that there is a significant difference between the mean salaries or the mean incomes of males and females. That is what you are concluding at 5% level of significance. Okay, so that is t-test, simple t-test. It is clear up to this point? Any questions?
No, sir. No, sir.
T-test you must have already studied in hypothesis testing or some other sessions also. You must have studied. So hopefully there are no questions and all of you know the concept well. So then our next concept or the next target technique is a one-way ANOVA. One-way ANOVA is required again when you have more than two groups. That is, if you have a minimum of three groups and you want to make the comparison in means, then you will analyze the problem through a one-way ANOVA. That is, you only have one factor. So which out of the two, subject or gender, contains more than two groups? That is subject. Subject has three categories in it, 1, 2, and 3. That is statistics, psychology, and political science. So if you make a if you want to make a comparison now on the basis of subject, one-way ANOVA based on subject, that is, we have three possibilities: statistics, political science, and psychology. Right? So the null hypothesis will be mu s is equals to mu ps is equals to mu p, and alternative will be uh, at least two mu's differ. Right. So at least two mu's differ. That is the alternative hypothesis. So this is run through one-way ANOVA, and the procedure is simple. Go to analyze, compare means, and then choose the bottom option, one-way ANOVA. Select that. So salary, you have to shift it to the dependent list, and subject, you have to shift it to the factor box, right? And in this, you do not have to choose any grouping variable or any 1, 2, 3. You do not have to define that. All you have to do is you require a post hoc test, because in case the null hypothesis is rejected, you want to find out where the exact difference is lying. So click on post hoc and choose Tukey. You can also choose Bonferroni and Sheffy also. Those are also providing good results. And but I for this particular problem, I will be going with Tukey. Click on OK or continue. Then go to options. In options, what else do you require? You require the descriptive statistics. It is always important to look at the mean and the standard deviation of the columns. Then what else you require? You require the homogeneity of variance test. That is an assumption, right? So I will explain this Welch test later on. So click continue and then click OK. So this is the result. First of all, a descriptive table is provided. And in this descriptive table, we have the three rows: statistics, political science, and psychology. 40 values in each of the three groups, their particular mean, standard deviations, standard error, and then the confidence interval for mean, right? And test of homogeneity of variances. This is providing a non-significant p-value. That is, the null hypothesis is rejected. So homogeneity of variances, again a Levene test is used, and the p-value is 0.785, which is above 0.05, and you will accept the null hypothesis that all of the variances are equal, right? I've always mentioned the null hypothesis will always consider all are equal or there is no difference. So all variances are equal. This is a separate hypothesis for homogeneity of variance or a Levene statistic, right? So first assumption is met, normality is also met. We already know that the data is continuous, the groups are independent, all of the assumptions are met. The next ANOVA table is the main one, and in this you have two possibilities: between groups and within groups. You have a sum of squares, then you have degrees of freedom, then you have mean square, then an F value, and then SIG value. So all you need to look at is this SIG value, and it is not exactly 0. Now it is written 0, but it is only signifying that it is a very small value. There might be a value, it might consider up to 10, 20, 30 decimal places, but never say that p-value was equals to 0. P-value will never be equals to 0 for real life problems. When this shows 0.000, it means that the value is less than 5%, and it requires what? Or it suggests what? That the null hypothesis is rejected, and you conclude that there is a significant difference between the three groups. There is a significant difference between in the population means of the salaries of the three groups. That is statistics, political science, and psychology. Some of you might be wondering that the descriptive table, if you look at this, hopefully this is visible to everyone, right? All of you are there listening. Participants?
Yes, sir.
Okay. Now the first table of descriptive, this is providing the mean values and standard deviation. These are for the sample. We already have the sample. Therefore, this 75,000, 58,000, 68,000, these are sample values. Because the population values are unknown, we have everything about the sample, we can calculate from the sample. So the sample values will be known. So these are sample values, and from the sample values, you can see that there is a difference. But that is not strong enough evidence to suggest that the population values will also be different or not. That is why you require this ANOVA or a t-test, because you need to find out by running these statistical concepts that using the samples, what inferences you can make about the unknown population. So don't say that, or don't write anywhere that there is you can see that the difference is there between the mean values, and therefore there is a significant difference among the population values also. No, you can only suggest that according to p-value, but the mean values are based on sample. So those are only used for describing what your sample is. Right, so now you have rejected your null hypothesis and you have concluded the alternative hypothesis, this one, that at least two mu's differ. So where is that difference lying? Is it between mu-s and political science, or between stats and psychology, or between political science and psychology? So for that, you run a post hoc test. And we have chosen Tukey for that, and it is provided in this multiple comparison table. All you need to do is look at the combinations. Statistics, the first combination is with political science, and you check its SIG value, which is less than 5%. Then you look at the second row, statistics with psychology, and that is also the SIG value is again less than 5%. Similarly, political science with statistics, political science with psychology, all of the values are less than 5%. That means the results are significant. That means you can conclude that all of the three combinations are significant. That is, the population means are different for all of the three possibilities, the three combinations. You can say that, in other words, for this problem, mu s is not equals to mu political science, mu s is not equals to mu psychology, and mu political science is not equals to mu psychology. So according to post hoc multiple comparison, we have concluded that there is a significant difference in the average salaries for all of the three possibilities in the combinations of the subject. Subject wise, all of the three salaries are different, right? Statistics one is earning different from political science is earning different from psychology, and similarly statistics is earning different from psychology. So this is the conclusion of one-way ANOVA. In case the one-way ANOVA provided a non-significant result, that is the p-value was greater than 5%, then p-value would have provided a non-significant result. The post hoc test would have provided a non-significant p-value also for all of the possible combinations. Okay, so this covers one-way ANOVA. Hope it is clear. I mentioned about Welch ANOVA. So in case when we ran this homogeneity of variance test, in case this assumption was not met, what you were supposed to do is you were supposed to ignore the provided results at the bottom, because this homogeneity of variance test can only be provided by running this ANOVA. Right, so if this p-value was supposed less than 5% for this homogeneity of variance Levene statistic, then you have to run the ANOVA again. But how do you do that? You can run this previous command from here. You go to options and you select this Welch ANOVA. In that case only, this Welch ANOVA is robust to unequal variances. Right, Welch ANOVA is suitable when your variance assumption is not fulfilled, equal variance assumption is not fulfilled. Then you will have to run Welch ANOVA, and just in the end you have to run, or you have to check the p-value. Right, another option is when you go to post hoc, equal variance is not assumed, and you have to select Games-Howell. So in that case, you will have to check those particular p-values. So up to this point, it is clear, right? Hopefully.
Yes, sir.
I think only one participant is listening. What about the others?
Yes, sir.
Okay. So this covers one-way ANOVA. See, Welch ANOVA is used when your equality of variance assumption is not fulfilled, and that is obtained by the homogeneity of variance test by the Levene statistic in ANOVA. If this p-value was less than 5%, that means the equality of variance assumption is not fulfilled, and you have to apply alternatives then. So one alternative is you go to post hoc, and in the equal variance is not assumed, you run the Games-Howell test. You run the Games-Howell test, and that will provide you separate p-values for all of the possible combinations. Similar results will be provided, but it will be calculated using a different formula, considering that equal variances are not assumed. Okay, so one option is this. Another option is you go to options and you click on this Welch. So Welch ANOVA is not disturbed or is not changed according to equal variance assumption not being fulfilled. So if the equal variance is not fulfilled, you can run Welch ANOVA also. So this is the possibility, or the you need to remember every single concept. It is like you have the data. First of all, you need to check the assumptions, and you need to check which test will be most suitable for your particular data. All of these tests are available, but all of these tests are not applicable for your particular data. Now, for this example that I've shown you, it is a very simple type of example and all of the assumptions were met. But in real life problems, these assumptions might not meet. So in that case, you have to know the alternative solutions also. Okay, so this is about one-way ANOVA. So we need to move on to two-way ANOVA now, and we will be using the same data set. So we will be using the same data set, and if we have time, we will cover repeated measures. But I will only explain how you run the repeated measures ANOVA in SPSS. I do not have a particular data set at the moment, and I will show you the procedure for that if time persists. Yeah. So any questions up to this point before we move on to two-way ANOVA? Right. So moving on to two-way ANOVA. Again, now suppose that if you look at the original data set, this data set was divided according to income and divided according to three subjects and two categories of gender, males and females, and three subjects. Now, if you want, you have run, first I have shown you, if you want to analyze the income group according to gender only, then we ran a independent sample t-test. If you want to analyze according to subject, then one-way ANOVA was required because there are three categories and two sample t-test is not possible. But when you want to look at the combined effect, or suppose you want to look at the two factors combined or together, that is, you want to look at the effect of, you want to create a model which is considering the effect of both gender as well as the subject at the same time, then in that case you have to use a two-way ANOVA. And again, you will have to create your two set of hypotheses, which is according to the second model, mu plus alpha I plus beta j plus epsilon. Right? One set of hypotheses will be based on alpha, the second one will be based on beta. So in this case, one set of hypotheses will be based on gender and the other one will be based on subject. Right? But remember that gender only has two categories, but still we are using it in a two-way ANOVA. And I will show you that post hoc test will not be possible in that because there are only two categories. And SPSS will already provide you a warning that a post hoc test is not possible for two groups or gender analysis of income or salary. So you define your data like this again, and you have subject as well as gender. Then you go to analyze. Now this is different from one-way ANOVA. You go to analyze, then you go to general linear model and you select univariate. Okay, analyze general linear model and you select univariate. Univariate means that you only have one dependent variable. Okay, you only have one dependent variable, that is why you are selecting univariate. If you have more than one dependent variable, then you select the multivariate. So reset this and you select, this is what it will show. You select or transfer your salary variable to the dependent box. Subject will go in fixed factors and gender will also go in fixed factors. Define contrast. You just need to, you have many options available. One by one, you need to check them. And it is not required that you have to select anyone. It is not required. It is not compulsory to select all of them. Then you move on to plots. And this is required for testing a interaction. How many of you know about interaction? When running a two-way ANOVA, there are two concepts. One is main effect and one is to interaction effect. We only have half an hour left, so I will briefly explain this. Consider the two-way ANOVA. I will write it here. This was the two-way ANOVA model, right? Alpha, beta, and epsilon. Now here, alpha and beta, they are known as main effects. Okay? And suppose there is another possibility, there will be another model, yij is equals to mu plus alpha I plus beta j plus alpha beta ij and then plus epsilon ij. Okay? So we have added another term and this one is known as an interaction effect. That is, you are once you have analyzed the effects separately from suppose gender and subjects, those are the main effects. And one, if the interaction is there, if it is significant, only then you have to run this model, the second. Otherwise, if the interaction is not possible or if it is not significant, then there is no need and you can continue with your first model. So the interaction effect is this, that is, you are looking at gender and subject, the combined effect they are providing on the response, that is, the response is what? Income or salary. So the combined effect they are providing on income, that is provided by the significant interaction effect. If it is not significant, then no need to include it. And otherwise, what else you have is, you have the main effects of gender and subject and the individual effects of gender on income and the individual effects of uh, subject on income. Those are obtained from the main effects, right? So if you want to test the interaction effect, and this is required whenever you run a two-way ANOVA, so whenever you run that, you go to plots, select subject in the horizontal axis and gender in the separate line box, and then you click on add. So that will show you a subject into gender, similar to what? Alpha into beta. So subject into gender, and then you click OK or continue. Then select post hoc. For which variable do you require post hoc? For that variable which has more than two categories. So gender is not possible. Gender will not lie in that assumption. So, but if you select it, so you have to select subject in this, and then you can select Yuki. Same process, similar process to what we have done in the one way. If you select gender, it will show you a warning message that post hoc was not possible for gender because there are only two groups. And that is fine, because there are only two groups, males and females. Your null hypothesis will be mu m is equals to mu f, or they are both not equal. So you do not require any other possible combinations of analysis in gender. So you can remove that. Then click continue. In options, you require the homogeneity test. And if you want to display means for these, you can select these options, but not required. You can require the descriptive statistics, you can check that. And for current analysis, let us leave it up to this point. That's it. Continue. And that's right. So everything is done. You can click OK. And the heading will be univariate analysis of variance. The previous one was one way. And the second one, two-way ANOVA, is defined as, or the topic is written as, univariate analysis of variance. Ignore the first table, it just shows you how many values there are in each group, each category. Look at the second table, descriptive statistics. it shows you the mean values. Separately, statistics male, this much mean, statistics female, this much mean and standard deviations, and how many 20 values in each group. Then considering the second subject, political science, males and females, mean values separate for that, standard deviation separate for those. Similarly, last psychology, males and females, and then separately calculations has been done for mean and standard deviation, and then in the end the total, right? Levine's test for equality of variance, again, it provides you a non-significant, that is the null hypothesis is accepted, and it is also written at the bottom. Test the null hypothesis that the error variance of the dependent variable is equal across groups. That is your null hypothesis, that the error variance of the dependent variable across the groups, across all of the possible groups, they are all equal. That is your null hypothesis. Your dependent variable is the salary, right? Then it has shown you a model also. Model will be design is intercept plus subject plus gender plus subject into gender. So this is similar to the two-way ANOVA model, mu plus alpha plus beta plus alpha beta, right? Epsilon is not shown in the end results, and you must have studied this in regression. I will revise it in a few minutes. I think regression topic has been completed. I know that logistic has been completed, I think. Okay.
Done, sir.
Okay. So the model is mu plus alpha plus beta plus alpha beta plus epsilon. Epsilon is not shown in the final result because I will explain it here. Epsilon follows the assumption of normality with zero mean and constant variance. Okay. Constant variance is there. As written. So this zero mean, this is the mean of error. And when you consider the regression equation, y is equals to beta naught plus beta 1 x plus epsilon, in the end, whatever software you use, suppose height weight, you get weight is equals to 1.74 plus 0.76 into height, something like that. If you obtain a regression like that, regression result like that, there is no epsilon. Epsilon or error values are not provided. Why? Because the regression output, it provides you the average results. Expectation, there is a concept of expectation, and that signifies the average values. So the result of this equation, it is the average value. Average, in other words, is also known as mean, and the mean of error is zero. So when you take the expectation of this whole model, it is just a mathematical or statistical concept. If you take the expectation of this whole equation, epsilon will become zero. So that is why in the final equation of any regression or ANOVA, epsilon results or ANOVA or residuals or error values are not provided. Okay, so given values of x, this means that you're calculating the values of y, the response for given set of values of x. That is dependent value variable for given values of independent variable. Right, so coming back to this model, mu plus alpha plus alpha beta. This is written here, intercept plus subject plus gender plus subject into gender. This is that equation. So equality of variance is assumed because of this p-value. Then we move on to the second provided box, test of between subject effects, and you have to look at the p-values of everything that is provided. So second one, you have to look at intercept, that is significant, subject, that is significant, gender is significant, but the interaction between subject and gender, that is non-significant because the p-value is greater than 5%, 0.151. It is greater than 5%. So you accept the null hypothesis that the interaction effect is not significant. Okay, whereas the remaining p-values are all less than 5%, and that provides a significant result. That is, you reject the null hypothesis. And where is my word file? What was your null hypothesis? One was for alpha. This is alpha 1 is equals to alpha 2 is equals to alpha 3. Against the alternative for alpha, this is alpha i's are not equal, right? And then according to beta, that will be beta 1 is equals to beta 2, which was gender and which was that. If this is gender, beta 2 is gender, then beta, this will be beta 1 not equals to beta 2, because there are only two groups in gender and three groups in subject. So this is your hypothesis. In both of the hypotheses, both of the null hypotheses are rejected and your alternates are accepted. Alternative hypothesis, they are accepted, and both of them are concluded that the effects of alpha or subject are not equal across the groups, and the effect of gender are not equal across the groups. That is the effect, sorry, the average salaries or the average incomes are not equal across the groups for both subjects as well as gender. In other words, we can say that the effects of subject and effect of gender is significant. That is another way. There are three ways of writing your null and alternative hypothesis. It is very important that how you state these two statements. So the effects are significant, and the salaries are not equal across the groups. So since these are significant and the interaction effect is non-significant, therefore you will run a post hoc test for only subject, and that is providing, again, it is providing the same result as we have obtained for the one-way ANOVA. When we ran the one-way ANOVA for subject only, this was the same result we were obtaining. So you can say that the two-way ANOVA is an extension of one-way ANOVA. If suppose gender, we also include another third category, then either we run a two-way ANOVA for subject and gender and obtain a significant or a non-significant result for post hoc as well as the main effects. And another way is that you can run a one-way ANOVA twice, one for subject and one for gender. That is another possibility. This is the same concept which I explained, that you can run a t-test 3 times or you can run a one-way ANOVA once, right? Whichever saves you more time, you obviously have to do that. So when you run a one-way ANOVA once, another alternative is that you are running a t-test 3 times, right? Checking all of the 3 possible combinations of the hypothesis separately. And again, if your gender also has 3 categories, then your subject and gender will both have three categories, and you can run a one-way ANOVA separately for subject also and for gender also. Sorry. But why run a two-way ANOVA? Because we want to look at this interaction effect, whether that interaction effect is significant or not. The combined effect on the salary is significant or not. If that is what we are interested in, plus we want to save time, we are only running the two-way analysis once, or another option is run the one-way ANOVA twice, separately for subject and gender. Hope this difference is clear.
Yes, sir.
Right. And I want to show that this post hoc test, this is multiple comparison, or you can also say it as pairwise comparison. So it is looking at paired values. That is, once it is looking at statistics and political science, and once it is looking at statistics and psychology. So what is this when you are considering only two values? This post hoc test, in other words, it is also same as a t-test. So when you run a one-way ANOVA or a two-way ANOVA, and you run the post hoc test, you are running that one-way ANOVA, and separately you are also, when you run the post hoc test or a multiple comparison, you are separately running a t-test also. So this is same as a t-test. There is no difference. So either you run many times the t-test separately, or you run all of these ANOVA once, and you obtain the same results. So it saves you much more time. Hope this concept is clear. And we also made a plot also for interaction. Males and females, they are shown with blue and green line, and they are separate for statistics, political science, and psychology. Because the interaction is non-significant, you can also assess that by looking at this graph also. How? If there was an interaction, if there was a significant interaction between the two variables, that is subject and gender, then these lines would have interacted somewhere. There would have been some intersection point also between these lines. But since there is no intersection between the two lines, then we consider it to be as non-significant. And this is just a graphical interpretation. So this completes two-way ANOVA. So we have completed one-way ANOVA and we have completed two-way ANOVA. Okay, what else? So up to this point, are there any questions or doubts, any queries which you want to ask?
No, sir.
How many of you are from agriculture background? Okay, how many of you have heard of design of experiments or experimental designs concept, CRD, RBD? Have you heard of these?
No, sir.
Sorry, can you please repeat?
No, sir.
Okay. If if you ever come across agricultural concepts, then CRD, completely randomized design, or randomized block design, they are both the same as a one-way ANOVA and a two-way ANOVA. The ANOVA table which was created here, one-way ANOVA table, this is the same as that obtained for a CRD. Now CRD, if I want to explain,
Sir, will
we
you
have,
explain repeated measures in theory?
I will explain. I will quickly explain that. CRD and RBD, we have two concepts. This is the concept of one way and this is the concept of two way. And in this, we have the same ANOVA table. Same ANOVA table which we have obtained in the outputs of one way and through SPSS, the same ANOVA table we have also. But we have sources of variation, and this might be separate. For suppose we were testing subjects, then we can have, in this case we have treatments, or we can skip this part because we have to cover that repeated measures also. So repeated measures, how you run this, if I create a separate one, suppose we have this salary, right? And suppose, let me first explain. Now, I don't know what that result will provide. It might provide a non-significant result or a significant, because I have not tested that data yet. That is the data for a two-way ANOVA. But still, we have, it is good to understand that topic. So, okay. Last topic is repeated measures ANOVA, and this is an extension of pair t-test. And all of these tests we have covered today are all parametric. So pair t-test, this is used when you have two values before and after. That is, you only have two time points. Right. So t-test was also, independent sample t-test was also used when you only have two groups. Pair t-test is also used when you only have two time points before and after, but the individuals are same. Suppose that when you have readings or values from more than two time points, suppose time point 1, time point 2, and time point 3. You have readings you have collected for 20 individuals. 20 individuals, you have collected the readings, suppose today, then after 2 weeks, and then after 5 weeks. So this is today, this is 2 weeks, and this is 5 weeks. Okay, so you have considered, and this is for the same up to 20 individuals. That same individual has been asked or interviewed about his reading thrice, 3 times. That is today, 2 weeks, and then after 5 weeks. So you have three set of points. Now three separate time points. If you have more than three, that is also fine. You can have four, you can have five, you can have six, seven, eight, as many as you want. And this is also possible for two-way ANOVA, three-way ANOVA, as many groups as you can have. Even if you have one-way ANOVA, that is used when you have more than two groups. If you want to compare the means for more than two groups, then you apply one-way ANOVA. I'm explaining in a simple manner. You have more than two groups, then you apply one-way ANOVA, and that means more than two groups can be possible for 3, 4, 5, 6, 7, 8, 9, 10, as many as you want. Right. So this is similar for pair t-test, and in case we have this data, this was used for checking the normality of the three salary groups, right? According to statistics, psychology, and political science. Now, let me change this. Again, for paired t-test as well as repeated measures ANOVA, the assumption of normality needs to be met, needs to be fulfilled. So we know that all of these three variables, they're following normal distribution. But now I will not consider to be these subjects. This is suppose reading at week 1. This is suppose reading at week 4. And this is suppose reading at week 7. Right? Might be wrong, because again I want to analyze the result. It's not wrong, but it's just that it might not provide a significant result if you want to compare the means. So what will be your null hypothesis? For pair t-test, your null hypothesis will be mu mu for before is equals to mu for after, and alternative will be mu before is not equals to mu after. Or in pair t-test, we generally avoid using the two-tailed test or the not equals to. In general, we use either less than or greater than, because this is an information about something before and after. So something has happened, and that is causing some changes in the after values. So if the after values are greater than the before values, then your result is appropriate. Or if the after values are suppose less, pair t-test is used in diet program. Diet program problems are very common. A person goes on a diet, he notes down his weight today, and then he notes after going a diet or exercise or whatever regime he's following, he then again notes his weight after suppose 4 weeks in the next month, right? So before and after value. So if the after weight is less as compared to the before weight, that means that the diet program was successful. So in that case, greater and less than signs are more appropriate. So when you have a repeated measures ANOVA, that means it is an extension of pair t-test, and your null hypothesis will be mu at week 1. This is equals to mu at week, what have we taken? Whatever we have taken, suppose week 4 we have taken, and mu at week 7, I think. And then the alternative will be at least 2 are different, right? So normality assumption is met. You go to analyze, you go to general. If you want to run a paired t-test, you go to compare means, and you run paired sample t-test, right? So you only have in this, you do not, in this method, you do not have to write all of the salaries in one single column and the second categorical variable has to be there. No, in this, all of the three columns can be separate. So if I want to make a comparison about week 1 and week 4, I shift week 1 and then week 4 will be separate in there. And I click OK. And this output is obtain here. T-test for paired sample. So we have the mean values for week 1, week 4. We have the correlation. Correlation is only 0.255, but we have to look at the paired sample result, and that is providing a significant value of 0.000 or less than 5%. So that means that if there is a difference in the salaries, or sorry, we're not talking about salaries now. Let us suppose there is something else, right? So there, the week 1 values and the week 4 values are separate. There is a significant difference between the two. So this was for paired t-test when you only have to make the comparisons pairwise. And you can also run this for all of the three possible combinations. Week 1 again you shift with week 7, then week 4 with week 7. So you can make all of the three possible combinations at once, and then you click OK, and that will provide you all of the mean values, correlations, and at the end, the significant results. So there is a significant result between all of the week 1s, and week 4 and week 1 with week 7, and then week 4 with week 7, right? So this is running the paired t-test 3 times. Otherwise, we can run a repeated measures ANOVA. So you go back to your data set, go to analyze, general linear model, and at the bottom it says repeated measures. You select that. Here you have to define number of we are writing week factor 1. Let us write that as week, and number of levels, there are 3. Then you click add, and then you define Okay, is it clear up to this? I'll repeat. General linear model, repeated measures, define week here. You can write any name which you want. Okay, it is already defined. Then you write 3 here and then you click on add. It is already added, so I'm not clicking there. Then you have to click on define. Remove this. Now you define. So now new box will open, and in this you have to make the possible combinations, what time points you want, right? So if you select week 1 first, then week 4, and then week 7, you select all of those. Then in post hoc, there are no categorical, nothing is available, so you cancel that. Plots, I don't want any plot in this, and plus in options, I only want the homogeneity test and the descriptive statistics. If we want to make a comparison, this is the place, because post hoc test nothing was available there. So you select week, you compare mean effects, and you select Bonferroni. This is the other technique which I mentioned apart from Tukey, which you can apply. So Bonferroni is another method. Another tests are also possible here. So Bonferroni, and then you click OK. No other requirement is there. Click continue and then OK. So hopefully this will provide the results. Ignore the warning. It says that homogeneity specification is ignored. So we will also ignore it. Then descriptive. Now there are lots of assumptions for a repeated measures ANOVA, but the main table which you have to look at is the test of within subject and the test of between subject. The last table, the test of between subjects, this will provide you the significant result output. Okay, this is suggesting that all of the 3 week points, the week 1, week 4, and week 7, they are all separate, they are all different, they are all significant, right? But the previous tables, those are all significant. Those are all important to look at also. This multivariate test, if you have to consider this, now in some cases we want the p-value to be greater, we want the null hypothesis to be accepted. Wilks lambda is used that your 3 groups, they are properly divided. That is your week 1, week 4, week 7, all of the 3 groups are properly divided. The values of the continuous data, they are all properly distributed among the 3 groups, right? This is the first table. The second is Mosh test of sphericity. Sphericity means that, again, the assumption of equality of variance. So the t-test, or the p-value is providing a non-significant. This is what we require. It says that test the null hypothesis that the error covariance matrix dependent is proportional to an identity matrix. Ignore what it says. Just this is similar. Sphericity means the equality of variance assumption. So if it is again similar to what we have run for one-way and two-way, this is again suggesting that equality of variance is there among the 3 groups, so we can move on. If this is not possible, we have to look at the alternatives. Then these are some additional test. This is comparing the within subjects effects. So they are all significant. And you do not have to consider all of the 4. This is some additional information. Now I've already mentioned SPSS provides you many additional information which is not required. You are obtaining the results from other sources also, so you just consider those. Keep your analysis basic and don't make it too complex. So then all of the results are significant here. And here we have, again, within subject contrast, that is not required. This is between subjects, which is significant. Again, this is significant. And in the end, this is the pairwise comparison, which we have obtained from running that Bonferroni. Remember that we have, I'll show you again, repeated measures. You define it, and you go to options, and here you have to select that week and shifted display means for select this compare mean effects and then select Bonferroni. This is provide you a similar result to pairwise comparison, because our repeated measures ANOVA is providing a significant result. That is, it is rejecting the null hypothesis, it is rejecting this, and it is accepting the alternative that there are differences somewhere among the 3 groups. Where are the differences lying? You can obtain that by running that Bonferroni test, and Bonferroni test, and that will provide your pairwise comparison, and all of the week 1 with week 2, week 1 with week 3, similarly week 2 with week 3. All of the others are repetitive, and all of the p-values are significant, right? So this is the complete analysis of repeated measures ANOVA. You use it as an extension of pair t-test, and this covers the repeated measures ANOVA, this covers two-way ANOVA, one-way ANOVA. So we have covered all of the topics successfully, so that is good, and still 3 minutes are remaining.
Did you explain the RBTs little bit?
Okay. What are you saying? Sorry, please repeat.
RBTs are agricultural block, random block design.
Mhm.
Explain.
RBD is similar to two-way ANOVA. In RBD, you can say that randomized block design. So it uses the concept of mu plus alpha. I'm not writing those ij's, and epsilon. This is RBD because you have two-way ANOVA. One is for treatments. This is used in agriculture. Treatments means fertilizers. And one is for blocks. Suppose you divide your entire agriculture field, your whole cropping area, according to the fertilizers being used. Suppose if there are 4 fertilizers, then you divide your area according to blocks. In case to increase homogeneity of the soil. In case some area of the agriculture part is having more fertile soil, then you know that the crops will be grown at a much better rate, or more output or more yield will be provided. So in order, if the heterogeneity is there, that is your entire agricultural area is not homogeneous, then you divide your homogeneous or heterogeneous area into homogeneous blocks, and then you apply a randomized block design, right? So this is the same as a two-way ANOVA, and it will provide you that exact ANOVA table, which we have already discussed. CRD, which is one-way ANOVA, it is because it is one way, so therefore it will only consider alpha and only treatments. That is fertilizers. You divide your agricultural area according to the fertilizers being used. So if suppose you have 5 type of fertilizers and you distribute that accordingly to suppose 20 crops, so 5 will be divided accordingly to 5, 4, 4 for each. 4 crops will receive every type of fertilizer, right? Because you have 5. So this is the concept of CRD and RBD, and it is related to agricultural. Whoever or those participants that are from agricultural background, it is important for them, but you do not need to know anything else. One-way ANOVA, two-way ANOVA, that is all the concept you need to require, what we have studied in this 2-hour session. That is all which is required. And separately, you can apply this type of data if you have suppose a given data of 2 variables. You can extend this easily to a 3-factor ANOVA, that is 3-way ANOVA, but that will make it more complex. In case there was a significant interaction effect, then that would have also been included in the final model. Alpha beta would have been included, and you have to say that the interaction effect is significant, and that it implies that both subject and gender, if you think about it logically, subject and gender, they're not having an interaction effect. That is, they're not having a significant interaction effect. This is what we have observed. And that is also true, because it doesn't matter your salary. Suppose if you're talking about marks or salary, it doesn't depend on gender or subjects. There's not a combined effect. Suppose we are talking about marks, so gender is not going to distribute your whether you're going to obtain high marks or low marks. It is the number of hours which you study. So that is a separate variable which you have to include. Number of hours is more reliable or more relatable as compared to gender. So that is why if you include, instead of gender, if you include a subject, that is, suppose you take maths, physics, and statistics, and suppose you another variable you take is number of hours which you have studied. So those will have both of them, number of hours and the subject. Those will have a significant interaction effect, because that will be more highly significant. That will be more combined effect will be more easily provided then. So I hope that all of the concepts are clear. Just revise it, what we have studied today. And if you don't revise it, remember there are